Hi, my name is Jinxu Xiang, and this is my project presentation. I chose the course project to detect the cancer area. I will introduce my project through slide and my code in this order: cropping images, building data pipeline, modifying model, creating the loss functions, and predicting. The data we have has multiple resolutions. I use a level 2, 4, and 6 in my model. There are several ways on cropping the data. I use this way. First, I set the primary image's resolution to 256 times 256. Then I move the windows with a 192 pixels distance on both width and height. I also add a small random movement on each window, so all the positions of the whole image will be covered, and they are not completely parallel. To reduce the calculation and abandon the useless images like this white area, I remove the background patches like the tutorial. A better place to crop images is in local computer. Then we can zip the data together and upload it to Google Drive. Once we need to use the data, we can move the zip file to the workplace and unzip it to use the images. This will reduce the time to call the data. This is my cropping step codes. Crop image data will crop one images and corresponding masks. This is a level 2 images from the whole image, level 4 and level 6. This function will crop multiple images. If we have generated the data before and we want to generate new one, we need to delete the files before generating new data. This function will do this. After cropping the data, we need to build a pipeline like this. This is my data generator. First, select one image from the files and use one data augmentation measure. After select batch size data, I use 32 as my batch size. Return the image and the corresponding masks. I use 3 levels of data. Their resolution is 256, 64, and 16. They all show the same area, but one pixel in level 6 contains more information. Next is the model part. I modified the UNet model on my project. The UNet architecture looks like a U, which justifies its name. This architecture consists of 3 sections: the contraction, the bottleneck, and the expansion section. This is my model. There are 3 inputs: input 1, 2, and 3, and 3 outputs: 1, 2, and 3, corresponding to the images and masks from 3 levels. Take input 1 as an example. The input shape is 32, 256, 256, and 3. Here 32 is the bench size, and I will omit it later. I first use the convolution 2D to change the last dimension to 16, and then use the max pooling 2D to change it to 128, 128, and 16. Then convolute it double the last dimension and doing max pooling again until the input shape become 32, 32, 122. Doing this on input 2 and we can get 32, 32, 32 data. Then we can concatenate them together to this and concatenate the input from input 3 together. So the bottleneck dimension become 16, 16, and 352. Next, I use the convolution 2D transpose and the convolution 2D to reduce the last dimension and extract a branch at the right time as the output of the corresponding input. Because the tumor area occupies a small proportion in the whole image, we can't directly use binary cross-entropy loss. I change the loss like this. If a cancer area is predicted to a normal area, the loss is 12 times greater than the normal area is predicted to the cancer area. Here using 12 is because normal area is about 12 times than the cancer area in average. Then for different level inputs, like input 1 and input 2, since they contain different information and the resolution for the small level image is small, there will be a larger coefficient on the loss for the low level inputs. This is the model part. I do this on Google Colab. First, I moved the unzipped data at each time. Then I build a data generator and returns 3 inputs and 3 outputs. This is my data generator. First, select 1 images and corresponding masks. Then use the data augmentation on it and return the inputs and outputs. This is my changed UNet model. I also printed the dimension of my model in each layer to help me to build and modify it. This is the loss function, and this is the model plot as shown in the slide. This is a way to build a data pipeline. Then I trained the data for at least 50 epochs. The last thing is to predict a whole image on a test image. I use a sliding distance of 128, which is half of the resolution of level 2 image, on width and height to crop the data. That means every pixel of the data will be predicted 4 times in different positions of the image. This is the result of image 110, which is the same as the example shown in the introduction before. The predicted model is close to the true model. This is the prediction, and this is the mask. I got 95.8% true positive accuracy, which is the predict accuracy of the cancer area of this yellow area, and 99.2% true negative accuracy is the predict accuracy on this purple area. For this image 91, although the predictions at the mask looks very closely, but the true positive is only 87.6%. The predicting ability of this model on some images still need to be improved. Maybe training more epochs or expanding the training set can solve this problem. This code is for the prediction. First, I load the data and the model and copy the data to the bench size input formula and predict each corped data. Since the predicted images is on level 2 and it's too large to output, I resize it to level 5 and plot it. The images I use in the slide comes from those functions. Finally, is the conclusion. First, I crop the data, image, and masks, and use them on a model for training. Then I crop the test image and predict the whole cancer area, and calculate some metrics for analysis. This is my presentation. Thank you.